Yeah, so the same holds true, of course, for a spherical range query, so instead of a cubical range query, so the same as for nearest neighbor queries. So we expect that if we do an arbitrary range query, we expect no points to be in this range query. Yeah? So with increasing dimensionality, the center of the hypercube, or more generally the center of the data space, becomes less important, and the volume of the data space concentrates on its borders, on its corners. Yeah? So randomly distributed points tend to be on the border of the data space, not in the center of the data space. Yeah? And yeah, this obviously seems to be a distortion of the space compared to our 3D way of thinking, as it's stated here. So compared to our intuition, what happens in 1 dimensions, 2 dimensions, maybe also in 3 dimensions. But once again, that's actually what it is. That's exactly what's stated here. Yeah? So that brings us to these empty spaces, and especially to these tails of the distribution. Yeah? So it means that the tails of a distribution become extremely important. Yeah? So if we consider standard density function f with, well, f hat here is 0 if the standard density function is below 0.01. Yeah? And if it's fx else, yeah, so meaning that, okay, we record for f hat here in these areas here we record a 0, and for all the other points, so we just cut the tails here of the distribution actually and set it to 0. Yeah. So if we rescale f hat to a density function, that will make very little difference in 1D, obviously, because we just cut out the things here which are below 0.01, which is somewhere here maybe, and somewhere here. Yeah. So if we just do that with a one-dimensional density function, or in a one-dimensional case, which is this one here, for example, it would not make a big difference to take either f hat or f, yeah, because we just cut out those things that are absolutely unimportant anyway, at least in 1 dimensions. But if we do that for high-dimensional data, we see that more than a half of the data has less than 1 times 100, so 1% of the maximum density function. Yeah, for if the expected value is 0. Yeah. So for example, in 10-dimensional Gaussian distribution, x, if we take the ratio between some observation from x, the density distribution of some observation times the density of or around 0, it'll be e to the power of minus something, which is, and the something is dependent on chi squared, the chi squared distribution. And the median of the chi squared distribution is 9.34. So the median of this ratio here is something like e to the power of, okay, minus chi squared, so that is 9 times 9.34 times 2, yeah, which is roughly this one here. Yeah. So most objects occur at the tails of the distribution actually, or in other words, in contrast to the low dimensional case where we think or we know that most of the music is playing around the mean, in high dimensional cases, regions of relatively low density can be extremely important parts. So now in high dimensional cases, the music is playing down here, not I have to say down here and not down here, but here and here. Yeah. So at the tails of the data space actually. So this is just the probability distribution. That is the data space here, and there is a one-dimensional data space, and that is how a Gaussian distribution looks like. That's in 1 dimensions, but not in high dimensions. Yeah, that's the point. And you see that here with an example. So you see the probability density functions, the radius of a sphere, yeah, around the mean value, and you see here, for example, a specific radius here of this sphere here, which is visualized here. So in 1 dimensions, it would be the entire probability within this sphere would be the integral from here to here of the probability density function. So basically the area which is highlighted here in red, which is pretty much a pretty high portion of the entire probability density, which is in the end 100%, of course. Yeah? In 2 dimensions, again, already a little less. Yeah, so that would be everything which is down here, which is already a little less. And for 10 dimensions, it's almost 0. Yeah? And for 20 dimensions, at least, it's extremely close to 0. Yeah? So just reporting what is down here, in 1 dimensions, 90% of the mass of the distribution lies between minus 1.6 and plus 1.6. Yeah, so somewhere between here and here. In 10 dimensions, which is down here, 99% of the mass of the distribution is at points whose distance from the origin is greater than 1.6. So here is most of the music playing. In that case here, most of the music is playing around here, which here is the mean. This is distance 0 to the mean. This is distance 1.6 to the mean. Yeah? So in low dimensions, most of the points are somewhere here or have distances lower than 1.6 to the mean. In 10 dimensions, most of the points have a distance much higher than 1.6 to the mean. And in 20 dimensions, even more, and so on and so on. Yeah? So in 10 dimensions, even 99% of the mass of the points. Yeah? So it's very difficult to estimate actually the density, except for a very large sample, because in very high dimensional spaces, most of the sample will be at the tails of the distribution. Yeah? So the Gaussian distributions are extremely flat. Yeah? So they are not really like reversing the whole shape basically, but they are extremely flat. Extremely flat. Last but not least, there are some further problems we just want to mention here. So patterns and models in high dimensional data are often hard to interpret, especially if we have long decision rules, because we have a lot of dimensions and features. Then we have long decision rules, and that means that the interpretation of these decision rules, of course, are a little less than if they are small and, kurz und knackig in German. So yeah, somehow intuitive also. Efficiency in high dimensional space is often limited. Of course, we have index structures to search for things, but these typically degenerate for high dimensional spaces. That's not our deal here, but just that you know. And distance computations are, of course, also a little bit more expensive because you just have to compute more. Yeah, there may be different semantic layers. We just talked about the baby game, where we had just different semantic layers in the different features, and patterns might only be observable in one specific subset of features. We talk about subspaces or projected spaces. So that is what we did with the baby game. Cliques of correlated features may dominate an object description. So correlation among features is always something which is typically not nice, and we will see how to take care actually about correlated features. So we'll talk about that later on also.